We're embarking on a voyage to a realm so magnificent, so utterly alien, that it challenges everything we thought we knew about worlds beyond our own. We're traveling to the moons of Jupiter, those celestial companions that dance around the solar system's giant in a cosmic ballet that has been unfolding for billions of years. Before we launch into this adventure, I'd love to know where you're watching from tonight. Feel free to drop your location in the comments below. There's something beautifully poetic about contemplating these distant worlds while we're all scattered across our own small planet, each of us gazing up at the same stars that have witnessed the birth and evolution of these remarkable moons. If you find comfort in these gentle explorations of the cosmos, I'd be incredibly grateful if you'd consider subscribing and giving this video a thumbs up. The visuals are here to guide you through this journey, but there's absolutely no pressure to keep your eyes open throughout. Feel free to close them, take a deep breath, and let your imagination soar alongside me as we venture into the realm of Jupiter's family of moons. Sometimes the most profound discoveries happen when we allow our minds to wander freely through the vastness of space. These aren't just any moons. These are worlds in their own right, each one unique, each one harboring secrets that have taken humanity centuries to begin unraveling. Some harbor vast oceans beneath frozen shells, oceans that may contain more water than all of Earth's seas combined. Others spew sulfur into space from hundreds of active volcanoes, painting their surfaces in brilliant yellows and oranges. Still others bear the scars of billions of years of cosmic bombardment, their faces telling the story of our solar system's violent past. What makes this journey truly remarkable is that we're living in the most exciting era of Jovian exploration in human history. Right now, as you listen to these words, spacecraft are hurtling through the void toward Jupiter's domain. The Europa Clipper, launched just recently in October 2024, is racing toward an encounter with one of the most promising worlds for life beyond Earth. The European Space Agency's JUICE mission, already on its way since April 2023, will arrive in 2031 to conduct the first orbital mission around another planet's moon since we orbited our own. But here's what makes this story truly captivating. Each of Jupiter's major moons exists in its own unique relationship with the giant planet, shaped by forces so powerful they defy our earthly experience. The closer a moon orbits to Jupiter, the more dramatically it's transformed by the planet's immense gravitational pull. It's like a cosmic forge, where proximity to the giant determines whether a world becomes a frozen ancient relic or a dynamic, actively changing landscape. The 4 largest moons, discovered by Galileo himself over 4 centuries ago, form a miniature solar system unlike anything else we know. They're called the Galilean moons, and they represent 4 completely different approaches to being a world. Moving outward from Jupiter, we encounter Io, a sulfur-spewing volcanic nightmare, where the ground literally moves beneath your feet. Then Europa, wrapped in ice, but hiding a global ocean that may be more hospitable to life than anywhere else we know. Ganymede follows, the largest moon in our entire solar system, bigger even than the planet Mercury, with its own magnetic field and mysterious grooved terrain. Finally, Callisto sits in the outer realm, an ancient battered world that serves as a museum of cosmic impacts, its surface unchanged for billions of years. What's truly mind-bending is how these worlds influence each other through a cosmic dance called orbital resonance. For every 4 times Io completes an orbit around Jupiter, Europa orbits exactly twice, and Ganymede orbits once. This isn't coincidence. It's a gravitational symphony that has been playing for billions of years, with each moon tugging on its neighbors in a precise mathematical relationship that keeps their orbits slightly elliptical, ensuring that the tidal forces from Jupiter continue to knead their interiors like cosmic dough. These tidal forces are beyond anything we experience on Earth. While our moon creates tides that move our oceans by a few feet, Jupiter's immense mass creates tides in solid rock that can lift the surface of its moons by hundreds of feet. Imagine standing on Io and watching the ground beneath your feet rise and fall by the height of a 30-story building twice each day. This constant flexing generates enormous heat through friction, melting rock, and creating the most volcanically active world we know. But the story gets even more extraordinary when we consider the radiation environment that bathes these moons. Jupiter's magnetic field is nearly 20,000 times stronger than Earth's, creating radiation belts so intense that they would kill an unprotected human in hours. This invisible storm of charged particles constantly bombards the moons, particularly the inner ones, chemically altering their surfaces and creating some of the most extreme conditions anywhere in our solar system. The spacecraft venturing into this hostile environment must be engineered like cosmic armor. They carry thick-walled vaults made of titanium and aluminum, protecting their delicate electronics from the relentless particle bombardment. Even with this protection, mission planners must carefully choreograph each spacecraft's path to minimize exposure while still gathering the scientific data we crave. Europa Clipper, our newest ambassador to the Jovian system, will perform an intricate dance around Jupiter, swooping in for close encounters with Europa before retreating to safer distances. During its mission, it will conduct 49 close flybys of Europa, some passing just 16 miles above the moon's icy surface. Each encounter will peel back another layer of mystery surrounding this ocean world that may harbor conditions suitable for life. The JUICE mission takes a different approach, planning to visit multiple moons before settling into orbit around Ganymede. This will mark the first time in human history that we've placed a spacecraft in orbit around a moon other than our own. For 9 months, JUICE will study Ganymede from orbit, mapping its internal structure and probing the secrets of its subsurface ocean with unprecedented detail. What drives us to undertake these ambitious missions? It's the tantalizing possibility that we may not be alone in the universe. These icy moons, with their hidden oceans kept liquid by tidal heating, represent some of the most promising places to search for life beyond Earth. Europa's ocean may contain twice as much water as all of Earth's oceans combined, and it's been liquid for billions of years. That's an almost incomprehensibly vast laboratory where the chemistry of life could have had eons to develop. The implications are staggering. If life exists in Europa's dark ocean, or in the subsurface seas of Ganymede or Callisto, it would represent a completely independent genesis of biology. Life that arose separately from terrestrial life, possibly following entirely different biochemical pathways, adapting to conditions we can barely imagine. Such a discovery would fundamentally transform our understanding of life's prevalence in the universe and our own place within the cosmic story. But these moons fascinate us for reasons beyond astrobiology. They're natural laboratories for understanding planetary formation and evolution. Ganymede's magnetic field tells us about the dynamics of its molten core, Europa's fractured ice shell reveals the complex interplay between its ocean and the surface above. Io's volcanic activity provides a window into processes that may have shaped the early Earth. Callisto's ancient cratered surface preserves a record of the solar system's violent youth, when impacts were common and catastrophic. Each world represents a different experiment in planetary science, shaped by its distance from Jupiter and its place in the gravitational dance of the system. By studying them, we learn not just about these fascinating worlds themselves, but about the fundamental processes that create and modify planets throughout the universe. The journey to Jupiter's moons is more than a scientific endeavor. It's a testament to human curiosity and our irrepressible desire to explore. 4 centuries ago, Galileo pointed his primitive telescope toward Jupiter and glimpsed these worlds for the first time, forever changing our understanding of our place in the cosmos. Today, we send sophisticated robots billions of miles to study these same worlds in exquisite detail, continuing that tradition of discovery that defines us as a species. As we prepare to delve deeper into each of these remarkable worlds, remember that you're part of this ongoing story of exploration. Every image returned by our spacecraft, every measurement taken, every mystery solved adds another page to humanity's greatest adventure. We're not just studying distant worlds. We're expanding the definition of what it means to be human in a universe filled with wonders beyond imagination. The dance of discovery continues as we venture deeper into Jupiter's gravitational embrace, where each moon tells a story written in ice and fire, in ancient scars and active geology. These worlds challenge our preconceptions about what it means to be a celestial body, existing in states so extreme and dynamic that they stretch the boundaries of planetary science itself. Consider for a moment the sheer scale of what we're witnessing. Jupiter's magnetosphere, that invisible bubble of magnetic influence surrounding the giant planet, extends outward for millions of miles. It's a structure so vast that if we could see it with our naked eyes, it would appear larger in our sky than the full moon, despite being hundreds of millions of miles away. Within this magnetic cocoon, the Galilean moons orbit like pearls on invisible strings, each one bathed in radiation and shaped by forces that would be utterly alien to any earthbound observer. The precision of their orbital ballet is breathtaking in its mathematical elegance. This resonance between Io, Europa, and Ganymede isn't just a curious coincidence. It's the result of billions of years of gravitational fine-tuning, where the moons have gradually adjusted their orbits until they achieved this perfect synchronization. The resonance acts like a cosmic metronome, ensuring that the tidal heating never stops, never allows these worlds to freeze into static, lifeless spheres. What emerges from this gravitational choreography is a gradient of worlds, each one a unique response to its position in Jupiter's influence. Moving inward from the relative calm of the outer system toward the giant planet is like descending into increasingly intense layers of a cosmic foundry. The transformation is remarkable. In the outer reaches, we find ancient, battered surfaces that have remained largely unchanged for billions of years. But as we spiral inward, the worlds become increasingly active, increasingly alive with geological processes. This gradient tells us something profound about planetary evolution. Distance doesn't just determine temperature, as it does in our relationship with the Sun. Around Jupiter, distance determines the very nature of a world's existence. It's a laboratory for understanding how gravitational forces can drive geological activity, how tidal heating can substitute for the radioactive decay that powers Earth's interior, how magnetic fields can shape not just the space around a planet, but the surfaces of distant moons. The radiation environment adds another layer of complexity to this already intricate system. Jupiter's magnetic field traps charged particles from the solar wind, accelerating them to incredible energies and creating radiation belts that dwarf anything in Earth's vicinity. These particles constantly rain down on the moons, particularly the inner ones, chemically processing their surfaces and creating compounds that would be impossible to form under normal circumstances. On Europa, this radiation bombardment may actually be beneficial for potential life. The energetic particles split water molecules on the surface, creating hydrogen peroxide and other oxidants that could eventually find their way into the subsurface ocean. There, they might provide the chemical energy that life forms could harness, creating a connection between the hostile radiation environment above and the potentially habitable ocean below. It's a reminder that in astrobiology, what seems destructive from one perspective might be life-giving from another. The engineering challenges posed by this environment push our spacecraft design capabilities to their absolute limits. Every component must be carefully selected and tested to withstand radiation doses that would destroy conventional electronics in minutes. The protective vaults housing the most sensitive instruments aren't just shields. They're survival capsules that allow our robotic explorers to function in one of the most hostile environments in the solar system. But perhaps the most remarkable aspect of our modern exploration of these worlds is how it builds upon centuries of gradual discovery. When Galileo first observed these moons through his telescope in 1610, they appeared as nothing more than tiny points of light that changed position from night to night. He had no way of knowing that he was looking at volcanic worlds, icy oceans, magnetic fields, and radiation belts. He simply saw that these objects orbited Jupiter, not Earth, and that single observation helped overturn humanity's understanding of our cosmic position. Each generation of observers has added new layers to our understanding. The advent of larger telescopes revealed surface features and hinted at compositions. Spacecraft missions transform these distant points of light into actual worlds with landscapes, atmospheres, and complex geological histories. Today's missions are pushing even further, probing beneath surfaces to map internal structures and search for the conditions that might support life. The current wave of missions represents perhaps the most ambitious phase yet of Jovian exploration. Europa Clipper's journey will take nearly 6 years, covering over 1 billion miles through the inner solar system. Its trajectory is a masterpiece of gravitational choreography, using encounters with Mars and Earth to adjust its path and arrive at Jupiter with the precise velocity needed for orbital insertion. Every aspect of its mission has been designed around the singular goal of determining whether Europa's hidden ocean could support life. JUICE's mission is equally ambitious, but takes a different approach. Rather than focusing intensively on a single moon, it will conduct a comprehensive survey of the entire Jovian system. Its instruments will peer through ice shells to map subsurface oceans, study the complex interactions between the Moon's and Jupiter's magnetic field, and investigate the processes that have shaped these worlds over billions of years. The mission's crowning achievement will be its orbital phase around Ganymede, where it will spend months conducting detailed studies impossible from flyby trajectories. The data these missions will return promises to revolutionize our understanding not just of Jupiter's moons, but of icy worlds throughout the solar system. Saturn's moons, Enceladus and Titan, with their own subsurface oceans and complex chemistry, will be viewed through the lens of what we learn at Jupiter. The discoveries may even inform our understanding of exoplanets, those distant worlds orbiting other stars, many of which may exist in similar relationships with giant planets. What makes these missions particularly exciting is their potential to answer questions that have tantalized scientists for decades. Does Europa's ocean connect to its surface through the cracks and ridges that crisscross its ice shell? What drives the geological activity that has resurfaced parts of Ganymede? How do the volcanic processes on Io compare to volcanism on Earth and other worlds? Are there chemical signatures in these environments that might indicate biological processes? The instruments aboard these spacecraft are marvels of miniaturized technology, each one designed to extract maximum scientific value from every precious encounter. Spectrometers will analyze the composition of surface materials and thin atmospheres. Radar systems will penetrate ice shells to reveal the structure of hidden oceans. Magnetometers will map magnetic fields and their interactions with charged particles. Cameras will capture images with resolution fine enough to reveal features smaller than a city block from hundreds of miles away. But beyond the technical achievements and scientific discoveries, these missions represent something even more profound about human nature. They embody our species' irrepressible drive to explore, to push beyond the boundaries of the known, to seek answers to questions that may not have practical applications, but satisfy something deep in our intellectual soul. The cost of these missions is measured in billions of dollars and decades of human effort. Yet we undertake them because they expand our understanding of what it means to exist in this universe. The moons of Jupiter serve as stepping stones in our expanding exploration of the cosmos. Each world we study, each mystery we solve, each question we answer prepares us for the greater challenges that lie ahead. The techniques we develop for studying Europa's ocean may one day be applied to studying oceans on worlds orbiting distant stars. The understanding we gain of tidal heating may help us identify potentially habitable worlds in other planetary systems. As we stand on the threshold of receiving unprecedented data from these remarkable worlds, we're reminded that exploration is never just about the destination. It's about the journey itself, the process of discovery that transforms not just our knowledge, but our perspective on our place in the cosmic order. These missions don't just study distant moons. They expand the definition of what we consider to be our cosmic neighborhood. The story of Jupiter's moons is ultimately our story as well, a chapter in the ongoing narrative of life's relationship with the cosmos. Whether or not we find evidence of biology in these distant oceans, we will certainly find evidence of the processes that shape worlds, that create the conditions where life might arise, that connect planetary systems across the galaxy through shared physical laws and evolutionary processes. Tonight, as we prepare to journey to each of these worlds individually, remember that we're not just passive observers of cosmic events happening billions of miles away. We're active participants in the greatest exploration program in human history, using the collective ingenuity of our species to extend our senses across the solar system and bring back knowledge that enriches us all. The story of each world begins with understanding the invisible threads that bind them to their giant parent. Jupiter's influence extends far beyond what we might imagine, creating a sphere of gravitational dominance that sculpts not just orbits, but the very essence of what these moons become. The tidal forces at work here operate on scales that dwarf anything we experience on Earth, generating internal heat through a process so efficient it has kept these worlds geologically active for billions of years. Picture the interior of Europa, where the constant kneading of Jupiter's gravity creates friction within the Moon's rocky core and icy mantle. This process generates enough heat to maintain a liquid ocean beneath miles of frozen surface ice. The ocean itself may be over 60 miles deep, creating a water reservoir that dwarfs all of Earth's oceans combined. But this isn't just any ocean. It's a dark, high-pressure environment that has remained liquid and stable for potentially billions of years, providing exactly the kind of long-term stability that complex chemistry requires to flourish. The surface of Europa tells its own fascinating story through the intricate network of ridges and cracks that crisscross its icy shell like a frozen highway system. These features aren't static scars, but active geological processes, evidence that the ocean below continues to influence the world above. Some scientists theorize that these ridges form when warm water from below rises through the ice, creating pressure that fractures the surface and allows fresh material to emerge. If true, this process could be delivering nutrients and energy from the ocean to the surface, creating a dynamic interface between two very different environments. What makes Europa particularly intriguing is the possibility that its ocean may be in direct contact with a rocky seafloor. This connection could provide the chemical ingredients necessary for life, as minerals from the rocky interior dissolve into the water, creating a rich soup of elements and compounds. Combined with the energy provided by tidal heating and possibly even hydrothermal vents on the ocean floor, Europa presents a scenario remarkably similar to the conditions where life first arose on Earth. The radiation bombardment that constantly strikes Europa's surface adds another layer of complexity to this already intricate system. While this radiation would be lethal to any surface life as we know it, it may actually contribute to the habitability of the hidden ocean below. The energetic particles split water molecules on the surface, creating hydrogen and oxygen that could eventually work their way down through cracks in the ice. This process might provide the chemical energy that life forms could exploit, creating a connection between the harsh surface environment and the potentially nurturing ocean beneath. Moving outward in our journey, we encounter Ganymede, a world so large it challenges our very definition of what constitutes a moon. With a diameter larger than Mercury, Ganymede is effectively a planet in its own right, complete with its own magnetic field generated by a molten iron core. This magnetic field creates a protective bubble around Ganymede, partially shielding it from Jupiter's intense radiation and creating its own unique space environment. Ganymede's surface presents a fascinating puzzle of geological history written in ice and rock. Roughly half of its terrain consists of dark, heavily cratered regions that date back billions of years, preserving a record of the early solar system when impacts were far more common than today. But interspersed with these ancient terrains are brighter, younger regions characterized by complex systems of ridges and grooves that speak to more recent geological activity. The grooved terrain on Ganymede represents some of the most mysterious landscapes in our solar system. These features suggest that the Moon's icy crust has been stretched and fractured by internal forces, possibly related to the same tidal heating that affects Europa, though to a lesser degree due to Ganymede's greater distance from Jupiter. The process that created these grooves may have involved the partial melting of subsurface ice layers, allowing the surface to shift and reform in ways that created the complex patterns we observe today. Beneath Ganymede's varied surface lies another hidden ocean, sandwiched between layers of different types of ice under enormous pressure. This ocean may be even larger than Europa's, though it's buried much deeper beneath the surface and likely has less interaction with the rocky interior. The presence of this ocean, inferred from magnetic field measurements and other data, makes Ganymede another potential harbour for life, though the conditions may be quite different from those on Europa. The existence of Ganymede's magnetic field raises fascinating questions about the Moon's internal structure and evolution. The generation of magnetic fields requires a conducting fluid in motion, typically molten iron in a planet's core. For Ganymede to maintain such a field, it must have a partially molten iron core that's actively convecting, suggesting internal temperatures high enough to keep metal liquid despite the Moon's great distance from the Sun. Continuing our outward journey, we reach Callisto, perhaps the most enigmatic of Jupiter's large moons. At first glance, Callisto appears to be the least interesting of the Galilean moons, its surface uniformly dark and more heavily cratered than any other object in the solar system. But this apparent simplicity masks a complex interior structure that challenges our understanding of how icy moons form and evolve. Callisto's surface is a museum of cosmic impacts, preserving craters that date back nearly to the formation of the solar system itself. Unlike the other Galilean moons, Callisto shows no evidence of the geological resurfacing that has erased ancient craters elsewhere. Every impact, from massive basin-forming events to tiny meteorite strikes, remains visible on its battered face, creating a historical record of bombardment that spans billions of years. The preservation of this ancient surface tells us something important about Callisto's interior. Unlike its siblings closer to Jupiter, Callisto appears to have never undergone significant internal heating that would drive geological activity. Its greater distance from Jupiter means that tidal forces are much weaker, insufficient to generate the friction needed to melt ice and rock in its interior. Yet even Callisto holds surprises. Magnetic field measurements suggest that it too may harbour a subsurface ocean, though buried much deeper than those of Europa and Ganymede. This ocean, if it exists, would be separated from the surface by hundreds of miles of ice and rock, making it perhaps the most isolated, potentially habitable environment in the solar system. The contrast between these worlds illustrates one of the most beautiful principles in planetary science. Small changes in initial conditions, in this case orbital distance from Jupiter, can lead to dramatically different evolutionary paths. The same basic ingredients of ice, rock, and gravitational influence have created 4 completely distinct worlds, each one a unique experiment in planetary formation and evolution. As our robotic explorers prepare to study these worlds in unprecedented detail, they carry with them instruments designed to answer questions that have puzzled scientists for decades. How thick is Europa's ice shell, and does it connect directly to the ocean below? What processes created Ganymede's complex grooved terrain? How deep is Callisto's suspected ocean? And could it support life despite its isolation from the surface? The answers to these questions will reshape our understanding, not just of these specific worlds, but of icy moons throughout the solar system and beyond. Saturn's moon Enceladus, which spews water ice from its south polar region, operates under similar principles of tidal heating. Titan, with its thick atmosphere and methane lakes, represents yet another variation on the theme of how moons can evolve in the gravitational embrace of giant planets. The discoveries awaiting us at Jupiter may even inform our search for life around other stars. Many of the exoplanets we've discovered orbit close to their parent stars, making them unlikely candidates for life as we know it. But these planets may have moons, and those moons might exist in conditions similar to Europa or Ganymede, harboring oceans kept warm by tidal heating rather than stellar radiation. The implications extend beyond astrobiology to our fundamental understanding of planetary systems. The Jupiter system serves as a laboratory for studying how gravitational resonances form and evolve, how magnetic fields interact with charged particles, and how tidal forces can drive geological activity across billions of years. These processes operate throughout the universe, shaping planetary systems around countless other stars. What makes our current era of exploration particularly exciting is the convergence of multiple technological advances that allow us to study these worlds with unprecedented precision. Advanced spectrometers can identify specific chemical compounds from vast distances. Radar systems can peer through solid ice to map hidden oceans. Magnetometers can detect the subtle magnetic signatures that reveal internal structure and composition. The spacecraft themselves represent marvels of engineering, designed to operate in one of the most hostile environments imaginable, while maintaining the precision needed for delicate scientific measurements. Every component has been tested and retested to ensure it can survive years of radiation bombardment while delivering data across the vast distances that separate Jupiter from Earth. As we stand on the threshold of this new era of discovery, we're reminded that exploration is fundamentally about expanding the boundaries of the known. Each measurement taken, each image captured, each mystery solved adds to humanity's collective understanding of our cosmic environment. These missions don't just study distant worlds. They expand our definition of what constitutes our cosmic neighborhood and our place within it. The story of Jupiter's moons is ultimately a story about the incredible diversity that can arise from simple physical laws operating over vast spans of time. It's a reminder that the universe is far more creative and surprising than we often imagine, capable of producing environments and phenomena that stretch our understanding and challenge our preconceptions about what's possible. Our preconceptions about what's possible. As we continue our journey deeper into Jupiter's realm, we encounter the innermost of the Galilean moons, a world so dramatically different from its siblings that it might as well exist in an entirely separate universe. Here, in the closest orbit to the giant planet, we find Io, a moon that defies every expectation we might have about what a celestial body should be. Imagine standing on the surface of Io, though such a journey would be impossible for human explorers. The ground beneath your feet would literally be moving, rising and falling by hundreds of feet as Jupiter's immense gravitational pull kneads the moon's interior like cosmic dough. The landscape stretches before you in brilliant yellows, oranges, and reds, painted by sulfur compounds that have been ejected from hundreds of active volcanoes scattered across the surface. This is no ordinary volcanic activity. Io experiences volcanism on a scale that makes Earth's most dramatic eruptions look gentle by comparison. Plumes of sulfur and sulfur dioxide gas shoot hundreds of miles into space, creating umbrella-shaped clouds that can be seen from spacecraft millions of miles away. Some of these volcanic fountains reach heights that would extend far beyond Earth's atmosphere, powered by the incredible tidal forces that never cease their relentless work. The source of this extraordinary activity lies in Io's unique position within Jupiter's gravitational field. As the innermost Galilean moon, Io experiences tidal forces so intense that they completely dominate the moon's geology. The constant stretching and squeezing generates enough heat to keep Io's interior molten, creating a world where the surface is constantly being renewed by fresh volcanic material. What makes Io's volcanism particularly fascinating is its exotic chemistry. Unlike Earth's volcanoes, which primarily erupt silicate rocks and water vapor, Io's volcanoes spew sulfur and sulfur dioxide. This creates a landscape unlike anything else in our solar system, where sulfur flows like lava across the surface, creating frozen rivers and lakes of yellow and orange material that would be utterly alien to terrestrial eyes. The surface of Io is so young that virtually no impact craters remain visible. Any crater that forms is quickly buried or obliterated by fresh volcanic deposits, making Io's surface effectively brand new in geological terms. This constant resurfacing means that we're looking at a world that reinvents itself continuously, where the landscape you might observe today could be completely transformed within human lifetimes. But Io's influence extends far beyond its own small world. The volcanic activity continuously pumps material into space, creating a vast torus of charged particles that orbit Jupiter along Io's orbital path. This material becomes part of Jupiter's radiation environment, contributing to the intense particle bombardment that affects all the other moons in the system. The connection between Io and Jupiter is so intimate that it generates electrical currents flowing between the moon and the planet. These currents, carrying millions of amperes, create spectacular auroral displays in Jupiter's atmosphere directly connected to Io's position in its orbit. It's as if Io serves as a cosmic lighthouse, its volcanic activity creating a beam of charged particles that sweeps around Jupiter with each orbit. The extreme conditions on Io make it perhaps the most challenging target for spacecraft exploration. The radiation environment is so intense that electronics would be destroyed in hours without heavy shielding. The volcanic activity means that the surface is constantly changing, making it difficult to plan detailed studies of specific features. Yet these same extreme conditions make Io one of the most scientifically valuable targets in the solar system. Studying Io provides insights into volcanic processes that may have been common throughout the early solar system. The moon serves as a natural laboratory for understanding how tidal heating can drive geological activity, processes that may operate on exomoons orbiting giant planets around other stars. The exotic chemistry of sulfur volcanism offers clues about alternative forms of geological activity that might occur in environments very different from Earth. The volcanic plumes themselves are windows into Io's interior composition. By analyzing the materials ejected during eruptions, scientists can infer the chemical makeup of the moon's subsurface layers. Some eruptions appear to tap into deeper reservoirs than others, providing samples from different depths within Io's tortured interior. Moving beyond the Galilean moons, Jupiter hosts a vast collection of smaller satellites that tell their own fascinating stories. These minor moons fall into several distinct groups, each with characteristics that reveal different aspects of Jupiter's history and evolution. Some appear to be captured asteroids, irregular chunks of rock and ice that were snared by Jupiter's gravity as they wandered through the outer solar system. The irregular moons orbit in eccentric, highly inclined paths that bear no resemblance to the orderly dance of the Galilean satellites. Many travel in retrograde orbits, circling Jupiter in the opposite direction to the planet's rotation. This suggests they are indeed captured objects, former asteroids or comets that fell under Jupiter's gravitational influence and became permanent members of the system. These small moons provide crucial insights into the early history of the solar system. Their compositions and orbital characteristics preserve evidence of the chaotic period when planets were still forming and small bodies were scattered throughout the solar system by gravitational interactions. By studying Jupiter's irregular moons, we learn about the population of objects that existed in the outer solar system billions of years ago. Some of these minor moons may actually be fragments of larger objects that were shattered by collisions. Groups of small moons with similar orbits and compositions suggest they originated from the breakup of single larger bodies, creating families of related objects that share common origins. These collision events may have occurred relatively recently in astronomical terms, within the last few 100 million years. The study of Jupiter's complete moon system reveals the incredible complexity that can arise from gravitational interactions over billions of years. The regular satellites, including the Galilean moons, formed from a disk of material surrounding the young Jupiter, similar to how planets formed around the Sun. The irregular satellites represent later additions, captured during Jupiter's gravitational evolution as it interacted with the surrounding population of small bodies. This diversity makes Jupiter's system a natural laboratory for studying planetary formation processes. The regular moons show us how satellites can form in orderly systems, while the irregular moons demonstrate how gravitational capture can add complexity to planetary systems over time. Together, they provide a complete picture of how moon systems evolve and change throughout their history. The gravitational interactions within Jupiter's system continue to shape the orbits and characteristics of all its moons. The resonances that lock the Galilean moons into their precise orbital dance also affect the smaller satellites, creating gaps and clustering effects in the distribution of orbits. These gravitational resonances act like invisible barriers, preventing certain orbital configurations while promoting others. Understanding these complex gravitational relationships helps scientists predict the long-term evolution of the Jupiter system. Computer simulations can model how the moon's orbits will change over millions of years, revealing which satellites might eventually be lost to space and which will remain gravitationally bound to Jupiter. These same processes operate in exoplanetary systems, making Jupiter's moons a valuable analog for understanding how satellite systems evolve around planets throughout the galaxy. The magnetic environment around Jupiter adds another layer of complexity to the moon system. Each satellite experiences different magnetic field conditions depending on its orbit, creating unique space weather environments that affect surface chemistry and atmospheric processes. The charged particles trapped in Jupiter's magnetic field interact differently with each moon, depending on factors like orbital distance, size, and magnetic properties. Ganymede's magnetic field creates particularly complex interactions, forming a magnetic bubble within Jupiter's larger magnetosphere. This mini-magnetosphere partially protects Ganymede from Jupiter's radiation while creating its own unique particle environment. The boundaries between these magnetic regions shift and change as Ganymede orbits, creating dynamic conditions that vary with orbital position. Europa's interaction with Jupiter's magnetic field generates electrical currents within its subsurface ocean, providing one of the key pieces of evidence for the ocean's existence. As Europa moves through Jupiter's magnetic field, the conducting saltwater ocean experiences changing magnetic conditions that induce electrical currents. These currents create their own magnetic signatures that can be detected by spacecraft, revealing the presence of the hidden ocean without directly imaging it. These magnetic interactions also affect the chemistry of the Moon's surfaces and thin atmospheres. Charged particles from Jupiter's radiation belts bombard the surfaces, breaking apart molecules and creating new chemical compounds that wouldn't form under normal conditions. On Europa, this process may actually contribute to the potential habitability of the subsurface ocean by creating oxidants that could serve as energy sources for life. The thin atmospheres that surround some of Jupiter's moons are products of these same radiation processes. Io's atmosphere consists primarily of sulfur dioxide generated by volcanic outgassing, but it's continuously modified by particle bombardment from Jupiter's magnetosphere. Europa has a tenuous oxygen atmosphere created when radiation splits water molecules on its surface, while Ganymede and Callisto have trace atmospheres produced by the sublimation of water ice under particle bombardment. These atmospheric interactions create dynamic systems where the composition and density of each moon's atmosphere changes with its position in orbit around Jupiter. As a moon moves through different regions of Jupiter's magnetosphere, it experiences varying levels of particle bombardment, leading to cyclic changes in atmospheric properties that repeat with each orbit. The seasonal variations in these systems add yet another layer of complexity. Jupiter's 11-year orbit around the Sun creates long seasonal cycles that affect the entire Moon system. Changes in solar heating alter the balance between atmospheric production and loss, while variations in the solar wind modify Jupiter's magnetosphere and its interactions with the moons. Current and future missions to the Jupiter system will study these complex interactions with unprecedented precision. The instruments aboard Europa Clipper and JUICE are designed not just to map the moon's surfaces and interiors, but to understand how they interact with their environment. Magnetometers will trace the subtle magnetic signatures that reveal hidden oceans. Particle detectors will measure the radiation environment and its effects on surface chemistry. Spectrometers will analyze the composition of thin atmospheres and surface materials, altered by billions of years of particle bombardment. The data these missions return will transform our understanding of how moons evolve in the gravitational and magnetic embrace of giant planets. The insights gained at Jupiter will inform our interpretation of other moon systems throughout the solar system and help us understand similar processes that may operate around exoplanets orbiting distant stars. Perhaps most remarkably, these missions may answer one of humanity's most profound questions: about whether life exists beyond Earth. The conditions beneath the icy shells of Europa, Ganymede, and possibly Callisto represent some of the most promising environments for life that we know of anywhere in the universe. These hidden oceans have remained stable for billions of years, providing exactly the kind of long-term environmental stability that complex chemistry requires to flourish. The search for life in these environments pushes the boundaries of astrobiology into completely new territory. Unlike the search for life on Mars, which focuses on ancient traces of past biological activity, the search at Jupiter's moons looks for active, thriving ecosystems that may exist right now in the hidden oceans beneath our spacecraft's instruments. The implications of such a discovery would be staggering. Finding life in Europa's ocean would prove that biology can arise independently in multiple locations, suggesting that life may be far more common throughout the universe than we currently imagine. It would also demonstrate that habitable environments can exist in locations far from the traditional habitable zones around stars, expanding the number of potentially life-bearing worlds by orders of magnitude. But even if these missions don't detect signs of life, they will still revolutionize our understanding of habitability and the conditions necessary for biology to emerge and thrive. By studying the chemistry of these hidden oceans, the energy sources available to potential life forms, and the processes that deliver nutrients from the rocky interiors to the liquid environments, we'll develop a much more sophisticated understanding of what makes a world habitable. The journey to Jupiter's moons represents more than scientific exploration. It embodies humanity's deepest aspirations to understand our place in the cosmic order and to discover whether we share the universe with other forms of life. Each image returned, each measurement taken, each mystery solved brings us closer to answering questions that have haunted human imagination for millennia. As these robotic ambassadors race through the darkness toward their distant destinations, they carry with them not just sophisticated instruments, but the hopes and curiosity of an entire species. In studying these alien worlds, we're not just expanding our knowledge of planetary science and astrobiology. We're participating in the greatest adventure in human history, pushing the boundaries of the known and venturing into realms that challenge everything we thought we understood about what it means to be alive in this vast and mysterious universe. The moons of Jupiter await, each one a world unto itself, each one harboring secrets that have remained hidden since the dawn of the solar system. In just a few short years, we'll begin to unlock those secrets, and in doing so, we may discover that the universe is far more alive and vibrant than we ever dared to imagine. Imagine, the revelation that awaits us in Jupiter's realm extends far beyond the 4 giant worlds we've been exploring. As our spacecraft venture deeper into this cosmic theater, they encounter a universe of smaller actors, each playing crucial roles in the grand performance that has been unfolding for billions of years. These minor characters in Jupiter's story number in the dozens, perhaps hundreds, scattered throughout the gravitational domain of the giant planet, like cosmic confetti celebrating some ancient celestial event. Picture, if you will, the outer reaches of Jupiter's influence, where tiny worldlets follow eccentric paths through the darkness. These irregular moons dance to a different rhythm entirely, their orbits stretched into elongated ellipses that carry them millions of miles away from Jupiter, before sweeping them back toward their gravitational master. Some travel backward relative to Jupiter's rotation, cosmic rebels that refuse to follow the orderly progression of their larger siblings. These wayward satellites tell a story of cosmic violence and capture that spans the entire history of our solar system. They are likely refugees from the asteroid belt or the outer regions beyond Neptune, ancient wanderers that found themselves ensnared by Jupiter's immense gravitational web during close encounters that occurred millions or billions of years ago. Each one carries within its composition and orbital characteristics clues about the early solar system's chaotic youth. The process by which Jupiter captured these distant moons reveals something profound about planetary evolution. In the early solar system, when planets were still growing, and the space between them was filled with debris from planetary formation, gravitational encounters were common and often catastrophic. Jupiter, with its enormous mass and extensive sphere of influence, acted like a cosmic vacuum cleaner, sweeping up objects that ventured too close to escape. But capture is a delicate process that requires precise conditions. An object approaching Jupiter too quickly will simply swing around the planet and continue on its way into deep space. One moving too slowly will crash into the planet or be torn apart by tidal forces. Only objects with just the right velocity and trajectory can be captured into stable orbits, becoming permanent members of Jupiter's extended family. Some of these captured objects may have originally been binary systems, pairs of asteroids or small moons orbiting each other. The complex gravitational environment around Jupiter could have separated these pairs, capturing one member while sending the other careening back into interplanetary space. This process might explain some of the unusual orbital characteristics we observe among Jupiter's irregular satellites. The compositions of these minor moons provide windows into regions of the solar system far from Jupiter's current location. Some appear to be carbonaceous objects, similar to asteroids found in the outer reaches of the asteroid belt. Others show spectral signatures suggesting they originated even further out, perhaps in the region where comets form beyond Neptune's orbit. By studying these captured worlds, we're essentially examining samples from across the entire solar system, delivered to Jupiter's doorstep by billions of years of gravitational evolution. The collision history preserved in these small worlds tells another fascinating chapter of the Jupiter system's story. Many of the irregular moons appear to be fragments of larger objects that were shattered by high-velocity impacts. When two objects collide in the complex gravitational environment around Jupiter, the resulting fragments can end up in similar orbits, creating families of related moons that share common origins and compositions. These collision families reveal that the Jupiter system has remained dynamically active throughout its history. Even after the initial period of planetary formation ended, impacts continued to shape and reshape the satellite system. Some of these collisions may have occurred relatively recently in astronomical terms, within the last few 100 million years, suggesting that the Jupiter system continues to evolve and change even today. The study of impact families among Jupiter's moons provides crucial insights into collision processes throughout the solar system. The gravitational environment around Jupiter creates conditions that are difficult to replicate in laboratory experiments or computer simulations. By observing the actual results of collisions in this environment, scientists can test and refine their understanding of how impacts shape planetary systems. But these minor moons are more than just debris from ancient collisions. They serve as natural laboratories for studying processes that operate throughout the outer solar system. Their surfaces preserve records of bombardment by cosmic rays and solar wind particles that span millions or billions of years. The chemical changes induced by this bombardment reveal information about the radiation environment in the outer solar system and how it has changed over time. Some of these small worlds may harbor surprises that challenge our assumptions about where interesting chemistry can occur in planetary systems. While they lack the tidal heating that drives geological activity on the Galilean moons, they may still experience subtle chemical processes driven by radiation bombardment and the occasional impact event. These processes could create complex organic molecules in environments far removed from the traditional zones where we expect interesting chemistry to occur. The gravitational interactions between Jupiter's many moons create a web of relationships so complex that it challenges our computational abilities to fully understand. Each moon influences every other moon through gravitational perturbations that accumulate over millions of orbits. These interactions can gradually change orbital characteristics, moving moons into new resonances or ejecting them from the system entirely. The long-term stability of Jupiter's satellite system depends on a delicate balance between these competing gravitational influences. Computer simulations suggest that some of the current irregular satellites may be ejected from the system over the next few billion years, while others may spiral inward toward Jupiter and eventually be destroyed by tidal forces. The system we observe today represents just one moment in a continuous process of orbital evolution that will reshape Jupiter's family of moons over cosmic time. Understanding these complex gravitational relationships has implications far beyond the Jupiter system itself. Similar processes operate around other giant planets in our solar system and around exoplanets orbiting distant stars. The techniques developed for studying Jupiter's satellite system provide tools for understanding how moon systems evolve throughout the galaxy. The magnetic environment that permeates Jupiter's domain adds another layer of complexity to these already intricate relationships. Each moon experiences a unique magnetic environment depending on its orbital distance, inclination, and the properties of Jupiter's magnetic field at that location. This creates a diverse range of space weather conditions that affect surface chemistry, atmospheric processes, and the long-term evolution of each satellite. The interaction between Jupiter's magnetic field and the solar wind creates a dynamic system that changes with Jupiter's 11-year orbital period around the Sun. As Jupiter moves closer to and farther from the Sun, the balance between solar wind pressure and magnetic field strength shifts, altering the size and shape of the magnetosphere and changing the conditions experienced by all the moons. These variations create seasonal cycles in the Jupiter system that operate on timescales far longer than anything we experience on Earth. The changing magnetic environment affects the thin atmospheres that surround some of the moons, altering the balance between atmospheric production and loss processes. It also influences the rate at which charged particles bombard the surfaces, changing the pace of chemical evolution on these worlds. The upcoming missions to the Jupiter system will study these complex interactions with instruments designed to measure magnetic fields, particle populations, and their effects on the moons. The data they collect will provide the first comprehensive picture of how giant planet magnetospheres interact with their satellite systems, revealing processes that may be common around giant planets throughout the galaxy. But perhaps the most profound aspect of studying Jupiter's extended family of moons is what it tells us about the incredible diversity that can arise from simple physical laws operating over vast spans of time. Starting with the same basic ingredients of rock, ice, and gravitational influence, nature has created dozens of unique worlds, each with its own story, its own character, its own contribution to the grand symphony of planetary formation and evolution. This diversity challenges us to expand our definitions of what constitutes a world worthy of study and exploration. While the Galilean moons capture most of our attention with their dramatic geological activity and potential for harboring life, the smaller satellites remind us that every object in the solar system has something to teach us about the processes that shape planetary systems. The techniques we develop for studying these distant, challenging targets push the boundaries of space exploration technology. Designing instruments that can detect the subtle signatures of small, dark objects millions of miles away requires advances in sensitivity and precision that benefit all areas of astronomical research. The navigation techniques needed to visit multiple small targets during a single mission advance our capabilities for exploring complex systems throughout the solar system. As we stand on the threshold of a new era of exploration in the Jupiter system, we're reminded that discovery often comes from unexpected directions. While we focus our primary attention on the large moons, with their dramatic geological activity and potential for life, the smaller worlds may surprise us with their own unique contributions to our understanding of planetary science. The story of Jupiter's moons is ultimately a story about the power of gravity to create order from chaos, to sculpt beauty from violence, to generate complexity from simplicity. It's a reminder that the universe operates according to physical laws that are simultaneously elegant in their simplicity and breathtaking in their consequences. The same gravitational force that keeps us anchored to Earth's surface has created this magnificent system of worlds, each one a unique experiment in planetary formation and evolution. Every measurement our spacecraft make, every image they capture, every mystery they solve adds another verse to humanity's growing understanding of how planetary systems work. We're not just studying distant moons, we're deciphering the fundamental processes that create and modify worlds throughout the universe. The insights we gain at Jupiter will inform our understanding of moon systems around Saturn, Uranus, and Neptune, and help us interpret observations of exoplanetary systems orbiting distant stars. The human element in this grand exploration cannot be overlooked. Behind every spacecraft that ventures into the outer solar system lies decades of human ingenuity, creativity, and dedication. Teams of engineers solve unprecedented technical challenges to create instruments that can operate in environments no human will ever directly experience. Scientists develop new techniques for analyzing data that arrives years after the observations were made, carried across billions of miles by radio signals barely stronger than a whisper. The international collaboration required for these missions represents humanity at its finest, with nations that may have political differences working together toward common scientific goals. The knowledge gained belongs not to any single country or organization, but to all of humanity, expanding our collective understanding of our cosmic neighborhood and our place within it. As we prepare to receive the first detailed data from Europa Clipper, and JUICE in the years ahead, we're entering an era of discovery that may rival the great age of terrestrial exploration centuries ago. But instead of mapping unknown continents on our own planet, we're mapping unknown worlds in the realm of Jupiter, revealing landscapes and processes that no human imagination could have conceived without the guidance of scientific observation. The anticipation building within the scientific community is palpable, tempered by the knowledge that space exploration always brings surprises that challenge our preconceptions. The moons we think we understand may reveal unexpected complexities, while worlds we've dismissed as uninteresting may harbor the most profound discoveries of all. This journey to Jupiter's moons represents more than scientific exploration. It embodies the finest qualities of human nature. Our willingness to invest enormous resources and decades of effort to satisfy curiosity about worlds we may never visit speaks to something fundamental about what makes us human. We are explorers by nature, driven by an insatiable desire to understand the universe around us and our place within it. The story continues to unfold as our robotic ambassadors race through the darkness toward their distant rendezvous with these alien worlds. Each day brings them closer to their destinations, and each day brings us closer to answers that may transform our understanding of life, planetary formation, and the incredible diversity of worlds that populate our cosmic neighborhood. In studying Jupiter's moons, we're not just learning about distant objects in space, we're participating in the greatest adventure in human history, expanding the boundaries of the known and venturing into realms that test the limits of our imagination. The discoveries that await us in the Jupiter system may reshape our understanding of what it means to be alive in a universe filled with wonders beyond our wildest dreams. The dance of worlds around Jupiter continues, as it has for billions of years, indifferent to human observation, but rich with secrets waiting to be discovered. As we prepare to unlock those secrets, we stand on the threshold of revelations that may echo through human consciousness for generations to come, forever changing how we see ourselves and our place in the magnificent, mysterious, ever-unfolding story of the cosmos. Tonight, as we drift deeper into Jupiter's gravitational embrace, we encounter mysteries that challenge our most fundamental assumptions about what it means for a world to be alive. The boundary between living and dead becomes beautifully blurred when we consider that these moons exist in a state of perpetual transformation, shaped by forces so immense they dwarf anything we experience in our earthbound existence. Consider the profound intimacy of the relationship between Jupiter and its children. Every 2 days or so, Europa completes another orbit, its icy shell flexing and cracking under the relentless pull of its giant parent. The Moon doesn't simply orbit Jupiter, it dances with the planet in a gravitational waltz that has been choreographed by physics itself over billions of years. This isn't the distant, cold relationship we might imagine between celestial bodies, but something far more dynamic and immediate. The heat generated by this cosmic friction creates something almost miraculous. Deep beneath Europa's frozen surface, in an ocean that has never seen starlight, temperatures remain warm enough to sustain liquid water. This isn't just any water, but a vast sea that may have existed in liquid form longer than complex life has existed on Earth. While our planet's surface has been repeatedly sterilized by asteroid impacts and ice ages, Europa's hidden ocean has remained a stable, protected environment for potentially billions of years. What makes this even more extraordinary is that Europa's ocean isn't isolated from the chemical richness of the rocky interior below. Unlike a frozen lake on Earth, where ice simply caps liquid water, Europa's ocean likely sits directly atop a rocky seafloor. This creates the possibility of hydrothermal vents, underwater volcanic systems that could provide both the chemical ingredients and the energy that life requires to flourish. The parallels to Earth's own story are striking and humbling. Our planet's oceans may have been seeded by similar hydrothermal processes, where hot water rich in minerals and dissolved gases created the chemical conditions necessary for the first stirrings of biology. If Europa harbors life, it would represent not just a second genesis of biology in our solar system, but proof that the processes that created us operate throughout the cosmos. But Europa's potential for life extends beyond simple chemistry. The constant bombardment of radiation from Jupiter's magnetic field, while deadly to surface life as we know it, may actually contribute to the habitability of the hidden ocean below. This radiation splits water molecules on the surface, creating hydrogen peroxide and other compounds that could eventually work their way down through cracks in the ice shell. In the dark depths of Europa's ocean, these compounds could serve as sources of chemical energy for organisms that have never known sunlight. This creates a beautiful symmetry between destruction and creation, where the same radiation environment that makes Europa's surface utterly hostile to life may actually be feeding potential ecosystems in the ocean below. It's a reminder that habitability is often found in the most unexpected places, arising from the complex interplay of forces that initially appear destructive, but ultimately prove life-giving. Moving outward through Jupiter's realm, we encounter Ganymede, a world that defies easy categorization. Larger than the planet Mercury, possessed of its own magnetic field, harboring a subsurface ocean that may dwarf Europa's, Ganymede exists in a category all its own. This isn't simply a moon. It's a world that could easily be classified as a planet if it orbited the Sun directly, rather than dancing around Jupiter. The magnetic field generated by Ganymede's molten core creates a protective bubble within Jupiter's larger magnetosphere, partially shielding the Moon from the intense radiation that bathes the inner Jovian system. This magnetic cocoon may have profound implications for any life that might exist in Ganymede's buried ocean. The reduced radiation environment could allow for more complex chemistry, perhaps even creating conditions where organic molecules could survive and evolve over geological timescales. Ganymede's surface tells a story of geological violence and renewal that spans billions of years. The dark, heavily cratered terrain preserves impacts from the early solar system, when asteroids and comets bombarded the moons with devastating frequency. But interspersed with these ancient scars are brighter regions characterized by complex systems of ridges and grooves that speak to more recent geological activity. The creation of these grooved terrains required enormous forces, sufficient to crack and reshape Ganymede's icy crust over vast areas. The most likely explanation involves the same tidal heating that affects Europa, though operating at a reduced level due to Ganymede's greater distance from Jupiter. The process may have involved the partial melting of subsurface ice layers, allowing the surface to shift and reform in ways that created the intricate patterns we observe today. What emerges from studying Ganymede is a picture of a world caught between two states of being. Too distant from Jupiter to experience the intense tidal heating that drives Io's volcanic fury, yet too close to remain as geologically dormant as distant Callisto, Ganymede occupies a middle ground where geological processes operate at intermediate levels of intensity. This positioning has created a world of remarkable complexity, where ancient and modern terrains coexist in a patchwork that reveals different chapters of the Moon's long history. The subsurface ocean that likely exists within Ganymede presents its own unique characteristics. Buried deeper than Europa's ocean, and possibly sandwiched between different phases of ice under enormous pressure, this hidden sea may represent an entirely different type of potentially habitable environment. The conditions in Ganymede's ocean could be unlike anything that exists on Earth, creating opportunities for forms of chemistry and possibly biology that we can barely imagine. The pressure at the bottom of Ganymede's ocean may exceed that found in the deepest ocean trenches on Earth by orders of magnitude. Under such conditions, water itself behaves differently, potentially creating high-pressure forms of ice that could coexist with liquid water in ways impossible under terrestrial conditions. These extreme environments push the boundaries of what we consider habitable, forcing us to expand our definitions of where life might find a foothold. Continuing our journey outward, we reach Callisto, perhaps the most enigmatic member of Jupiter's family. This ancient world presents a surface so heavily cratered that it appears to be a museum of cosmic impacts, preserving the scars of bombardment that date back nearly to the formation of the solar system itself. Every major impact event is still visible on Callisto's battered face, creating a historical record of violence that spans billions of years. The preservation of this ancient surface tells us something profound about Callisto's interior evolution. Unlike its more active siblings, Callisto appears to have avoided the major episodes of geological resurfacing that have erased ancient craters elsewhere in the Jupiter system. Its greater distance from Jupiter means that tidal forces are insufficient to generate the internal heating needed to drive widespread geological activity. Yet even in this seemingly static world, surprises await. Magnetic field measurements suggest that Callisto, like its siblings, may harbor a subsurface ocean buried deep beneath its cratered surface. This ocean, if it exists, would be perhaps the most isolated, potentially habitable environment in the solar system, separated from the surface by hundreds of miles of ice and rock. The possibility of life in such an isolated environment challenges our understanding of what constitutes a viable habitat. Any organisms that might exist in Callisto's buried ocean would be completely cut off from surface processes, existing in a realm of perpetual darkness and isolation that has remained unchanged for billions of years. Such an environment might preserve forms of life that developed in the early solar system, creating a biological time capsule that could reveal the earliest stages of life's development in our cosmic neighborhood. The study of Callisto's ancient surface provides crucial insights into the bombardment history of the outer solar system. The density and size distribution of craters on Callisto's surface reveal information about the population of impacting objects that existed billions of years ago, when the solar system was young and chaotic. This information helps us understand the conditions that existed during the period when life was first emerging on Earth. The contrast between Callisto's pristine preservation of ancient surfaces and the active resurfacing occurring on the inner moons illustrates one of the most beautiful principles in planetary science. Distance from a gravitational source doesn't just determine temperature and orbital characteristics. It fundamentally shapes the evolutionary pathway that a world will follow throughout its existence. As we contemplate these four remarkable worlds, we begin to appreciate the elegant simplicity of the physical laws that have created such extraordinary diversity. The same gravitational forces that keep the moons in orbit also generate the tidal heating that drives geological activity. The same magnetic fields that create hazardous radiation environments also generate the chemical processes that could support life. The same impact events that scar ancient surfaces also deliver the raw materials from which new worlds can be built. The upcoming missions to the Jupiter system will study these relationships with unprecedented precision and detail. Europa Clipper's instruments are designed to peer through Europa's ice shell and map the hidden ocean beneath, determining its depth, salinity, and chemical composition. The spacecraft will search for plumes of water vapor that might be erupting from the surface, providing direct access to ocean materials without the need to drill through miles of ice. JUICE will take a broader approach, studying the entire Jupiter system during its 8-year journey through the realm of the giant planet. Its instruments will map the internal structure of multiple moons, trace the complex interactions between the moons and Jupiter's magnetic field, and search for signs of current geological activity across the satellite system. The mission's culmination will be the first orbital survey of Ganymede, providing 9 months of detailed observations that will revolutionize our understanding of this enigmatic world. The technical challenges overcome by these missions represent triumphs of human engineering and ingenuity. Designing instruments that can operate reliably in Jupiter's intense radiation environment required developing new materials and innovative shielding techniques. Creating navigation systems precise enough to guide spacecraft through close encounters with multiple targets demanded advances in computer modeling and trajectory planning that push the boundaries of what's possible. The data these missions will return promises to transform our understanding, not just of Jupiter's moons, but of icy worlds throughout the solar system and beyond. The techniques developed for studying subsurface oceans at Jupiter will be applicable to similar environments around Saturn, where moons like Enceladus and Titan harbor their own hidden seas. The insights gained about tidal heating and geological activity will inform our understanding of exomoons orbiting giant planets around distant stars. But perhaps the most profound impact of these missions will be their contribution to our understanding of life's potential prevalence in the universe. If we discover evidence of biology in the hidden oceans of Europa, Ganymede, or Callisto, it will fundamentally alter our perspective on our place in the cosmic order. Life would no longer be a rare accident confined to the narrow habitable zone around our sun, but a natural consequence of physical and chemical processes that operate throughout the galaxy. Even if these missions don't detect signs of life, they will still advance our understanding of habitability in ways that will guide future searches for life throughout the cosmos. By studying the chemistry of these subsurface oceans, the energy sources available to potential organisms, and the processes that maintain habitable conditions over geological time, we'll develop a more sophisticated framework for identifying potentially life-bearing worlds around other stars. The journey to Jupiter's moons represents more than scientific exploration. It embodies humanity's deepest aspirations to understand our cosmic context and to discover whether we share the universe with other forms of consciousness. These missions carry with them not just sophisticated instruments, but the hopes and curiosity of our entire species, representing our collective desire to push beyond the boundaries of the known and venture into realms that challenge our understanding of what's possible. As these robotic ambassadors race through the darkness toward their distant rendezvous, they participate in a story that began with Galileo's first telescopic observations over 4 centuries ago. Each generation of explorers has added new chapters to our understanding of these distant worlds, transforming them from points of light in Galileo's eyepiece into complex, dynamic environments that may harbor some of the most profound secrets in our solar system. The discoveries that await us in the Jupiter system may answer questions that have haunted human consciousness since we first looked up at the night sky and wondered whether we are alone. But they will also certainly raise new questions that we haven't yet learned to ask, opening new frontiers of exploration that will inspire future generations of scientists and dreamers. Tonight, as you settle deeper into contemplation of these cosmic mysteries, remember that you are witnessing one of the most extraordinary chapters in the history of human exploration. We stand on the threshold of discoveries that may rival those of Galileo himself, poised to extend our understanding into realms that exist at the very limits of what we can currently imagine. The moons of Jupiter await our arrival, each one a world unto itself, each one harboring secrets that have remained hidden since the dawn of the solar system. In just a few short years, our robotic explorers will begin to unlock those secrets, and in doing so, they may reveal that the universe is far more alive, far more vibrant, and far more filled with possibility than we ever dared to dream. The story continues to unfold in the darkness between worlds, where distance is measured not in miles, but in years of patient travel, where discoveries await that may echo through human consciousness for generations to come. As we drift towards sleep, carried by the gentle rhythm of our own breathing, we can rest knowing that somewhere in the void, our mechanical ambassadors continue their journey toward revelations that may forever change how we understand our place in this magnificent, mysterious, ever-unfolding cosmic dance. The profound silence that exists between these worlds carries its own form of communication, a cosmic whisper that speaks of processes so ancient and fundamental that they predate the emergence of life itself. As we drift deeper into this realm of perpetual motion and change, we begin to understand that the story of Jupiter's moons is ultimately a story about time itself, about how the patient accumulation of small forces over billions of years can create landscapes and environments that challenge everything we thought we knew about the possibilities inherent in planetary formation. Consider the delicate balance that maintains Europa's hidden ocean in its liquid state. This isn't simply a matter of internal heating keeping water from freezing. The chemistry occurring in this buried sea represents one of the most complex and sustained chemical experiments in our solar system. For billions of years, minerals from Europa's rocky core have been dissolving into the overlying water, creating a rich broth of dissolved salts and trace elements that could provide the fundamental building blocks for biological processes. The interaction between this mineral-rich water and the overlying ice shell creates conditions unlike anything we observe on Earth. As the ocean circulates beneath the ice, driven by the same tidal forces that flex the moon's interior, it carries dissolved materials upward toward the frozen boundary above. There, In the interface between liquid and solid, complex chemical reactions may be occurring that we're only beginning to understand. The fractures and ridges that crisscross Europa's surface aren't merely geological curiosities. They represent active pathways through which the hidden ocean below may communicate with the space environment above. When these cracks open and close under tidal stress, they may allow small amounts of ocean water to reach the surface, where the extreme cold and vacuum of space instantly flash. Freeze the liquid into ice crystals that record the chemical composition of the sea below. Some of these surface features appear remarkably young in geological terms, suggesting that the process of ocean surface interaction may be ongoing even today. If our spacecraft can analyze the composition of these fresh ice deposits, they may provide direct access to Europa's ocean chemistry without requiring the enormous technical challenge of drilling through miles of solid ice. The radiation environment that bathes Europa's surface, while hostile to life as we know it, may actually serve as a vast chemical processing plant that creates compounds essential for biological processes. The energetic particles that constantly bombard the surface don't just destroy, they also create, breaking apart simple molecules and reassembling them into more complex forms that could eventually find their way into the ocean below. This process of radiolysis creates a steady supply of oxidizing compounds that could serve as energy sources for chemosynthetic organisms, life forms that derive energy from chemical reactions rather than sunlight. On Earth, similar organisms thrive around hydrothermal vents in the deep ocean, creating entire ecosystems in regions of perpetual darkness. Europa's ocean may harbor similar communities, sustained by the chemical energy provided by the interaction between Jupiter's radiation and the Moon's surface ice. The magnetic signatures detected during spacecraft flybys of Europa provide tantalizing hints about the electrical conductivity of the hidden ocean. A perfectly pure water ocean would be a poor electrical conductor, but water rich in dissolved salts conducts electricity readily. The strength of the magnetic signals suggests that Europa's ocean may be quite salty, perhaps even more saline than Earth's oceans, creating an environment where complex chemistry could flourish. But the story of Europa's ocean extends beyond simple chemistry to questions of circulation and mixing that could determine whether life could establish itself and spread throughout this hidden sea. Computer models suggest that the ocean may experience large-scale circulation patterns driven by the same tidal forces that heat the Moon's interior. These currents could transport nutrients and dissolved gases throughout the ocean, creating a dynamic environment where chemical gradients and energy sources are constantly shifting and mixing. The depth of Europa's ocean, potentially reaching down 60 miles or more beneath the ice shell, creates pressure conditions at the seafloor that exceed anything found in Earth's deepest ocean trenches. Under such extreme pressure, water itself behaves differently, potentially creating unique chemical environments where reactions could occur that are impossible under terrestrial conditions. If hydrothermal vents exist on Europa's seafloor, they would operate under pressure conditions so extreme that the physics of hot water circulation might be fundamentally different from what we observe on Earth. The minerals dissolved by these high-pressure hot springs could create chemical conditions unlike anything in our terrestrial experience, potentially providing energy sources and chemical building blocks for forms of life that operate according to biochemical principles we haven't yet discovered. Moving our attention to Ganymede, we encounter a world where complexity emerges from the interplay between multiple layers of geological history. The bright grooved terrain that characterizes much of Ganymede's surface represents some of the most mysterious landscapes in our solar system, created by processes that required enormous forces operating over vast timescales. The formation of these groove systems likely involved the complete reorganization of Ganymede's surface over areas spanning hundreds of miles. The parallel ridges and valleys that characterize these regions suggest that the moon's icy crust was subjected to extensional forces that pulled it apart, creating space for new material to well up from below and solidify into the complex patterns we observe today. This process of crustal renewal may have occurred episodically throughout Ganymede's history, with periods of intense geological activity alternating with longer intervals of relative quiescence. The driving force behind these episodes remains mysterious, but it likely involves the same tidal heating that affects Europa, operating at reduced intensity due to Ganymede's greater distance from Jupiter. The magnetic field generated by Ganymede's interior adds another layer of complexity to this already intricate world. The existence of this magnetic field tells us that Ganymede must have a partially molten metallic core that's actively convecting, generating electrical currents that create the magnetic signatures we detect from spacecraft. This requires internal temperatures high enough to keep iron liquid, despite Ganymede's great distance from the Sun. The interaction between Ganymede's magnetic field and Jupiter's much larger magnetosphere creates a complex electromagnetic environment around the Moon. This magnetic mini-magnetosphere partially deflects Jupiter's intense radiation, creating regions of relative safety where delicate chemical processes might occur without being disrupted by energetic particle bombardment. Within Ganymede's presumed subsurface ocean, the reduced radiation environment might allow for the preservation and evolution of complex organic molecules over geological timescales. While Europa's ocean exists in a harsh radiation environment that constantly breaks down complex chemistry, Ganymede's ocean might serve as a more stable laboratory where intricate biochemical processes could develop and persist. The layered structure of Ganymede's interior, with multiple phases of ice existing under different pressure conditions, creates the possibility of chemical gradients and interfaces that don't exist in simpler ocean worlds. These boundaries between different phases of matter could serve as surfaces where complex chemistry occurs, potentially concentrating dissolved materials and creating conditions favorable for the emergence of self-organizing chemical systems. The great depth of Ganymede's ocean, possibly exceeding Europa's by a significant margin, creates an enormous volume of potentially habitable space. If life exists in this hidden sea, it would have access to chemical resources and living space that dwarf anything available in Europa's more constrained environment. Callisto presents us with perhaps the most profound mystery of all the Galilean moons. This ancient world, with its surface unchanged for billions of years, appears at first glance to be geologically dead. Yet the magnetic signatures detected during spacecraft encounters suggest that even this apparently static world may harbor a subsurface ocean buried deep beneath its heavily cratered surface. The implications of liquid water existing within Callisto are staggering when we consider the Moon's apparent lack of internal heating. Unlike Europa and Ganymede, which are kept warm by tidal flexing, Callisto orbits too far from Jupiter to experience significant tidal heating. If an ocean exists within this distant moon, it must be maintained by some other energy source, perhaps radioactive decay within Callisto's interior, or residual heat left over from the moon's formation billions of years ago. The ocean within Callisto, if it exists, would represent perhaps the most isolated, potentially habitable environment in our solar system, buried beneath hundreds of miles of ice and rock, completely cut off from surface processes and protected from Jupiter's radiation environment. This hidden sea would exist in conditions of perfect darkness and isolation that have remained unchanged for geological ages. Such an environment might preserve forms of chemistry or even biology that developed during the early history of the solar system, creating a time capsule that could reveal the conditions that existed when life was first emerging on Earth. Any organisms that might exist in Callisto's buried ocean would have had billions of years to adapt to conditions of complete isolation, potentially developing along evolutionary pathways completely unlike anything we observe in terrestrial biology. The study of Callisto's ancient surface provides crucial insights into the bombardment history that all the moons experienced during their early evolution. The preservation of craters dating back nearly to the formation of the solar system creates a detailed record of the impact flux that existed when the planets were young, and the space between them was filled with debris from planetary formation. This impact record reveals that the early solar system was a far more violent and chaotic place than the relatively peaceful environment we observe today. The frequency and intensity of impacts during the first billion years after solar system formation would have repeatedly sterilized any surfaces where life might have been trying to establish itself. Only in protected environments like subsurface oceans could early life have survived this period of intense bombardment. The differences between the 4 Galilean moons illustrate one of the most beautiful principles in planetary science: the idea that small differences in initial conditions can lead to dramatically different evolutionary outcomes. The relatively small differences in orbital distance from Jupiter have created 4 completely distinct worlds, each following its own unique pathway of development over billions of years. This sensitivity to initial conditions has profound implications for our understanding of planetary formation throughout the galaxy. If such diversity can arise from minor variations in orbital distance around a single planet, imagine the incredible variety of worlds that must exist among the thousands of exoplanetary systems we've discovered orbiting distant stars. The current missions racing toward Jupiter carry instruments designed to probe these worlds with unprecedented precision and sensitivity. Europa Clipper's ice-penetrating radar will map the thickness and structure of Europa's ice shell, revealing whether the ocean below connects directly to the surface through cracks and fissures. Its magnetometer will measure the electrical conductivity of the hidden ocean, providing crucial information about its salinity and chemical composition. The spacecraft's thermal imaging system will search for areas of unusual warmth on Europa's surface, potentially identifying locations where the ocean below lies closest to the surface, or where active geological processes are bringing warm material upward from the interior. These thermal anomalies could guide future missions to the most promising locations for detailed study or even sample collection. JUICE's comprehensive survey of the Jupiter system will provide the first systematic study of how these worlds interact with each other and with their electromagnetic environment. Its instruments will trace the flow of charged particles between the moons and Jupiter's magnetosphere, revealing how the radiation environment shapes surface chemistry and atmospheric processes on each world. The mission's gravitational studies will map the internal structure of multiple moons simultaneously, revealing the distribution of rock, ice, and liquid water within each world. These measurements will provide crucial constraints on models of internal heating and geological evolution, helping us understand how tidal forces have shaped these worlds over billions of years. The orbital phase around Ganymede will mark a historic milestone in planetary exploration, the first time we've placed a spacecraft in orbit around a moon other than our own. For 9 months, JUICE will study Ganymede from distances as close as a few hundred miles, mapping its surface composition, internal structure, and magnetic environment with exquisite detail. These orbital observations will reveal whether Ganymede's subsurface ocean connects to the surface through geological processes similar to those operating on Europa. They will map the three-dimensional structure of the Moon's magnetic field, providing insights into the dynamics of its molten core and the processes that generate planetary magnetism. The data returned by these missions will transform our understanding of habitability in the outer solar system and beyond. By studying how tidal heating maintains liquid water in environments far from stellar warmth, we'll develop new frameworks for identifying potentially habitable worlds around distant stars. The chemical signatures we detect in these subsurface oceans will guide our search for similar environments throughout the galaxy. But perhaps most importantly, these missions may answer the profound question of whether life exists beyond Earth. The instruments aboard Europa Clipper and JUICE are sensitive enough to detect the chemical signatures that biological processes would leave in these alien oceans. They can identify the organic compounds that serve as the building blocks of life, measure the chemical disequilibria that living organisms create in their environment, and search for the isotopic signatures that biological processes leave behind. The discovery of life in these hidden oceans would represent one of the most significant moments in human history, fundamentally altering our understanding of our place in the cosmos. It would prove that life can arise independently in multiple locations, suggesting that biology may be a common feature of planetary systems throughout the galaxy. Even if these missions don't detect definitive signs of life, they will still provide crucial information about the conditions necessary for habitability and the processes that maintain those conditions over geological time. This knowledge will inform our search for life throughout the cosmos, helping us identify the most promising targets for future exploration and study. The technical achievements represented by these missions push the boundaries of what's possible in space exploration. The spacecraft must survive years of exposure to Jupiter's intense radiation environment, while maintaining the precision needed for delicate scientific measurements. Their instruments must operate reliably across temperature ranges that span hundreds of degrees, from the frigid outer reaches of Jupiter's magnetosphere to the warmer regions closer to the planet. The communication systems must transmit detailed scientific data across distances of hundreds of millions of miles, requiring transmission powers and antenna designs that push the limits of current technology. The navigation systems must guide these spacecraft through gravitational fields so complex that they require constant course corrections and trajectory adjustments throughout the mission. The international collaboration required for these missions represents humanity at its finest, with scientists and engineers from dozens of countries working together toward common goals. The knowledge gained will belong not to any single nation or organization, but to all of humanity, expanding our collective understanding of the cosmos we inhabit. As we contemplate the profound implications of what these missions may discover, we're reminded that exploration is fundamentally about expanding the boundaries of human knowledge and understanding. Every measurement taken, every image captured, every mystery solved adds to the growing tapestry of human knowledge about our cosmic environment. The story of Jupiter's moons is ultimately our story as well, a chapter in the ongoing narrative of how intelligence emerged from the cosmos and began to study itself. We are temporary arrangements of atoms that have somehow become capable of contemplating our own origins, of building instruments that can extend our senses across the solar system, of asking questions about our place in the vast cosmic story. Tonight, as you drift towards sleep, remember that somewhere in the darkness between worlds, our robotic ambassadors continue their patient journey toward revelations that may echo through human consciousness for generations to come. They carry with them not just sophisticated instruments, but the hopes and dreams of our entire species, our collective desire to understand whether we are alone in this vast universe or part of a larger community of life that spans the cosmos. The discoveries that await us in the Jupiter system may answer questions that have haunted human imagination since we first looked up at the night sky and wondered about the lights moving among the stars. But they will also certainly raise new questions that we haven't yet learned to ask, opening new frontiers of exploration that will inspire future generations of dreamers and scientists. As you close your eyes and let the gentle rhythm of your breathing carry you toward rest, know that you are part of this grand story of discovery. Every person who has ever wondered about the cosmos, who has ever felt that sense of awe when contemplating the night sky, contributes to the human drive to explore and understand our cosmic neighborhood. The moons of Jupiter await our arrival, each one a laboratory for studying processes that operate throughout the universe, each one potentially harboring secrets about the nature of life itself. In just a few short years, we'll begin to unlock those secrets, and in doing so, we may discover that the cosmos is far more alive, far more connected, and far more filled with wonder than we ever imagined possible. Sweet dreams, fellow cosmic travelers. The universe continues its ancient dance around you, and you are part of that dance, now and always, in this magnificent, mysterious, ever-unfolding story of existence itself. The journey to Jupiter's moons is just beginning, and the best discoveries may still lie ahead, waiting in the darkness between worlds for curious minds to illuminate them with the light of understanding and wonder. The gentle gravitational embrace that holds these worlds in their eternal dance speaks to something far more profound than mere celestial mechanics. As we float deeper into this realm of perpetual twilight and wonder, we begin to understand that each of these moons exists not as isolated objects spinning through the void, but as integral parts of a vast living system where every component influences every other component in ways both subtle and dramatic. Picture yourself standing at the edge of Europa's fractured landscape, where the horizon curves away beneath an alien sky painted in hues of radiation and reflected starlight. The surface beneath your imagined feet tells stories written in languages of ice and time, each crack and ridge recording moments when the hidden ocean below reached upward toward the cosmos. leaving its signature in frozen testimony to the dynamic processes occurring far beneath. These surface features aren't merely geological curiosities frozen in time. They represent active conversations between the buried sea and the universe above, dialogues conducted through the medium of tidal stress and thermal expansion, where the moon's interior literally communicates with its surface through the vocabulary of fracture and renewal. Every ridge system, every chaotic terrain, every smooth plain speaks to different episodes in this ongoing conversation between the depths and the surface. The timescales involved in these processes stretch human comprehension almost beyond its limits. While we measure our lives in decades and our civilizations in centuries, these moons have been conducting their gravitational symphony for billions of years, each orbit adding another note to a composition so vast and complex that we've only recently begun to appreciate its beauty and intricacy. Consider the patience required for tidal heating to maintain liquid oceans beneath miles of solid ice for geological ages. This isn't a process that operates on human timescales, or even on the timescales of mountain building or continental drift. This is patience measured in billions of years, where the same fundamental forces that shape these worlds in their youth continue to operate with unwavering consistency across spans of time that encompass the entire history of complex life on Earth. The chemical processes occurring within these hidden seas operate according to this same vast temporal rhythm. Minerals dissolving from rocky cores, circulation patterns established over millions of years, chemical gradients maintained across oceanic basins larger than any terrestrial sea, all unfolding according to laws of physics and chemistry that remain constant across cosmic time. What emerges from contemplating these processes is a profound appreciation for the stability that characterizes these environments. While the surfaces of these moons may appear alien and hostile to our earthbound sensibilities, the conditions within their buried oceans may represent some of the most stable and persistent environments in our solar system. Protected from the chaos of asteroid impacts, shielded from the radiation storms that sweep through interplanetary space, insulated from the temperature variations that characterize surface environments. These hidden seas exist in states of equilibrium that have persisted longer than multicellular life has existed on our own planet. The spacecraft racing toward these distant worlds carry within their protective vaults instruments designed to peer through ice and rock and time itself, to reveal the secrets that have remained hidden since the solar system's youth. These mechanical explorers represent more than triumphs of engineering and navigation. They embody humanity's deepest aspirations to understand our cosmic context and to discover whether the processes that gave rise to life on Earth operate throughout the universe. The journey these robotic ambassadors are undertaking spans not just the vast distances between planets, but the conceptual distances between what we know and what we hope to discover. Every day of their multi-year voyage brings them closer to encounters that may fundamentally alter our understanding of life's prevalence in the cosmos, of the conditions necessary for habitability, of our own place in the grand scheme of cosmic evolution. The instruments aboard these spacecraft represent decades of human ingenuity focused on a single goal: the extension of our senses across impossible distances to touch and taste and analyze worlds we may never visit with human presence. Each spectrometer, each camera, each magnetometer has been designed and tested and calibrated to extract maximum scientific value from fleeting encounters with alien landscapes moving at thousands of miles per hour relative to the spacecraft. But perhaps the most remarkable aspect of these missions lies not in their technical sophistication, but in what they represent about human nature itself. The decision to invest billions of dollars and decades of human effort to satisfy curiosity about distant worlds speaks to something fundamental about what makes us human. We are explorers by nature, driven by an insatiable desire to understand the universe around us and our place within it. This drive to explore and understand connects us across all the barriers that typically divide human societies. The scientists and engineers working on these missions represent dozens of nationalities and cultures, united by shared curiosity about cosmic mysteries that transcend political boundaries and cultural differences. The knowledge they generate will belong not to any single group or nation, but to all humanity, expanding our collective understanding of the cosmos we inhabit. The data that will flow back from these missions over the coming years promises to transform multiple fields of scientific inquiry simultaneously. Planetary science will gain unprecedented insights into the processes that shape icy worlds throughout the solar system. Astrobiology will receive its first detailed look at environments beyond Earth where life might potentially flourish. Atmospheric science will study the thin atmospheres that surround some of these moons and the processes that maintain them. Magnetospheric physics will examine the complex interactions between planetary magnetic fields and the charged particle environments they create. But beyond these technical advances lies the possibility of discoveries that transcend scientific disciplines entirely. If these missions detect evidence of biological processes in the hidden oceans of Jupiter's moons, the implications will ripple through philosophy, theology, and human consciousness in ways we can barely anticipate. The confirmation that life has arisen independently in multiple locations within our solar system would suggest that biology may be a common feature of planetary systems throughout the galaxy. Such a discovery would fundamentally alter humanity's understanding of our cosmic significance. We would no longer be unique accidents of terrestrial chemistry, but representatives of processes that operate throughout the universe. The loneliness that has characterized human consciousness since we first realized the vastness of space would be replaced by the knowledge that we are part of a larger community of life that spans the cosmos. Even if these missions don't detect definitive signs of life, they will still provide crucial information about the boundary conditions for habitability and the processes that maintain those conditions over geological time. By studying the chemistry of these subsurface oceans, the energy sources available to potential organisms, and the mechanisms that transport materials between different regions of these alien seas, we'll develop more sophisticated frameworks for understanding what makes a world habitable. These insights will inform our interpretation of exoplanetary systems, where giant planets similar to Jupiter orbit distant stars and may host their own families of potentially habitable moons. The techniques we develop for studying tidal heating and subsurface oceans in the Jupiter system will be directly applicable to similar environments that may exist throughout the galaxy. The radiation environments that bathe these moons, while presenting enormous challenges for spacecraft operations, also provide natural laboratories for studying how energetic particles interact with planetary surfaces and atmospheres. The chemical processing that occurs when high-energy particles bombard ice and rock creates compounds that wouldn't form under normal circumstances, potentially providing energy sources and chemical building blocks that could support exotic forms of life. Understanding these radiation-driven chemical processes has implications that extend far beyond the Jupiter system. Similar interactions occur wherever high-energy particles encounter planetary surfaces, from the polar regions of Earth, where cosmic rays interact with our atmosphere, to the surfaces of exoplanets orbiting active stars. The insights gained from studying these processes at Jupiter will inform our understanding of space weather and its effects on planetary environments throughout the universe. The magnetic fields that permeate the Jupiter system create some of the most complex electromagnetic environments in our solar system. The interaction between Jupiter's powerful magnetic field and the smaller magnetic fields generated by some of its moons creates a hierarchy of magnetic structures that influence everything from particle trajectories to atmospheric chemistry. Studying these interactions provides insights into fundamental plasma physics processes that operate in environments ranging from planetary magnetospheres to stellar corona to the vast magnetic fields that thread through interstellar space. The gravitational relationships between Jupiter and its moons demonstrate the incredible precision with which celestial mechanics operates over cosmic time. The orbital resonances that lock the inner moons into their mathematical dance have remained stable for billions of years, testament to the reliability of the physical laws that govern planetary motion. These same resonances create the tidal heating that drives geological activity, connecting orbital dynamics directly to planetary evolution in ways that may be common throughout the galaxy. The diversity of outcomes we observe among Jupiter's moons, despite their formation from similar materials in the same environment, illustrates the sensitivity of planetary evolution to initial conditions. Small differences in mass, composition, or orbital characteristics can lead to dramatically different evolutionary pathways, creating the rich variety of worlds we observe today. This sensitivity suggests that planetary systems throughout the universe may exhibit similar diversity, with each system representing a unique experiment in planetary formation and evolution. As we prepare for the flood of data that will arrive when our spacecraft reach their destinations, we stand at the threshold of what may be the most transformative period in the history of planetary science. The discoveries awaiting us have the potential to answer some of humanity's most profound questions about our place in the cosmos, while simultaneously raising new questions we haven't yet learned to ask. The images that will arrive from Europa's fractured surface, the magnetic field measurements from Ganymede's interior, the compositional data from Callisto's ancient craters, all will contribute to a new understanding of how planets and moons evolve in the gravitational embrace of giant planets. Each measurement will add another piece to the growing puzzle of planetary formation and evolution, helping us understand not just these specific worlds, but the processes that shape planetary systems throughout the universe. The search for life in these alien oceans represents perhaps the most ambitious scientific undertaking in human history. We're not just looking for simple organic molecules or chemical signatures of biological processes. We're searching for entirely independent experiments in biology, potentially representing solutions to the challenges of life that differ fundamentally from the terrestrial approach we're familiar with. If life exists in these hidden seas, it may have evolved along pathways completely unlike anything we observe on Earth. The high-pressure, low-temperature conditions that characterize these environments could favor biochemical processes that operate according to principles we haven't yet discovered. The energy sources available in these dark oceans may support metabolic pathways that have no terrestrial analogues. The possibility that multiple independent origins of life exist within our solar system would revolutionize our understanding of biology itself. It would suggest that the emergence of life may be a natural consequence of certain chemical and physical conditions, rather than an extraordinarily unlikely accident that occurred only once in cosmic history. These missions also represent important steps toward eventual human exploration of the outer solar system. While the radiation environments around Jupiter make human visits extremely challenging with current technology, the knowledge gained from these robotic missions will inform the development of life support systems, radiation shielding, and spacecraft designs that could eventually enable human presence in these distant realms. The dream of human explorers, walking on the surfaces of these alien worlds, drilling through ice shells to sample subsurface oceans, establishing research stations in the outer solar system, may seem like distant fantasy today. But every great achievement in human exploration began with reconnaissance missions that mapped unknown territories and identified the challenges that would need to be overcome. Tonight, as you drift towards sleep, remember that you are witnessing one of the most extraordinary chapters in the human story. We are the first generation to possess the technology and knowledge necessary to study these distant worlds in detail, to search for life in alien oceans, to extend our understanding across the vast distances that separate planets. The spacecraft racing through the darkness toward their rendezvous with these alien worlds carry with them more than sophisticated instruments. They carry the dreams and aspirations of our entire species, our collective desire to understand our cosmic neighborhood and our place within it. Every successful measurement, every image transmitted across the solar system, every mystery solved represents a victory for human curiosity and ingenuity. The story of Jupiter's moons is still being written, with new chapters being added every day as our mechanical explorers draw closer to their destinations. The discoveries that await us may answer questions that have puzzled humanity for centuries, while opening entirely new realms of scientific inquiry that we haven't yet imagined. As you close your eyes and let the gentle rhythm of your breathing carry you toward rest, know that somewhere in the cosmic dark, patient robots continue their journey toward revelations that may echo through human consciousness for generations to come. They travel not just through space but through time, carrying our questions toward answers that may fundamentally alter how we understand life, planets, and our place in the magnificent, mysterious, ever-unfolding story of the universe itself. Sweet dreams, fellow travelers in this cosmic journey. The universe continues its ancient dance around you, and you are part of that dance, connected to distant moons and alien oceans, through the same physical laws that govern the beating of your heart and the firing of neurons in your dreaming brain. The best discoveries may still lie ahead, waiting in the darkness between worlds for curious minds to illuminate them with the light of understanding and wonder. The dance between anticipation and discovery reaches its crescendo as we contemplate what lies ahead in humanity's greatest voyage of exploration. The spacecraft that even now hurtle through the cosmic void toward Jupiter's realm carry within their protective shells more than just instruments and computers. They carry the accumulated wisdom of centuries of human curiosity, the refined techniques of decades of planetary exploration, and the hopes of a species that has always looked upward and wondered what secrets the darkness might hold. Picture the moment when Europa Clipper's cameras first resolved the intricate patterns of ridges and fractures that crisscross Europa's surface with clarity surpassing anything we've achieved before. Those images will arrive not as simple photographs, but as windows into processes that have been shaping this world for longer than complex life has existed on Earth. Each crack in the ice, each smooth plain between ancient ridges, each chaotic terrain where the surface has been completely reorganized will tell part of a story that spans geological ages. The radar signals that will penetrate Europa's ice shell represent perhaps the most ambitious attempt ever made to peer inside an alien world without physically traveling there. These electromagnetic pulses will slice through miles of frozen material, revealing the hidden architecture of the ice shell and mapping the boundary where solid meets liquid in Europa's buried sea. The returning echoes will carry information about ice thickness, internal structure, and perhaps even the chemical composition of the ocean that has remained hidden from human eyes since the solar system formed. When JUICE settles into its historic orbit around Ganymede, it will inaugurate a new era in planetary exploration. For the first time since the Apollo missions circled our own moon, a human-built spacecraft will orbit another world's natural satellite, conducting observations with a precision and continuity impossible during brief flyby encounters. The gravitational field measurements alone will revolutionize our understanding of Ganymede's internal structure, revealing how mass is distributed within this giant moon and providing clues about the processes that have shaped its evolution. The magnetic field mapping that JUICE will conduct represents a particularly elegant form of planetary archaeology. Ganymede's magnetic field, generated by convection in its molten core, carries signatures of the moon's thermal history, written in the patterns of its magnetic lines of force. By tracing these invisible field lines with exquisite precision, scientists will be able to infer conditions within Ganymede's deep interior and understand how this moon has evolved thermally over billions of years. But beyond the technical achievements and scientific discoveries lies something even more profound about what these missions represent. They embody humanity's willingness to invest enormous resources and decades of sustained effort to satisfy curiosity about places we may never visit with our physical presence. This commitment to exploration for its own sake, this dedication to understanding, rather than immediate practical application, speaks to the finest qualities of human nature. The international collaboration required to make these missions possible represents humanity at its most cooperative and visionary. Scientists and engineers from dozens of countries have worked together for decades to overcome the technical challenges posed by Jupiter's hostile environment. The knowledge they generate will belong not to any single nation or organization, but to all humanity, expanding our collective understanding of the cosmos we share. The data streams that will flow back from these missions over the coming years will be processed and analyzed by researchers around the world, each bringing their own expertise and perspective to bear on the cosmic puzzles these distant worlds present. Graduate students will write dissertations based on measurements taken in Jupiter's radiation-soaked environment. Established scientists will revise theories they've held for decades as new observations challenge existing models of planetary formation and evolution. The ripple effects of these discoveries will extend far beyond the scientific community. The images of alien landscapes, the detection of chemical signatures that might indicate biological processes, the mapping of subsurface oceans that dwarf Earth's seas, all will capture public imagination and inspire a new generation of explorers and scientists. Children who are just learning to read today may grow up to design missions to Saturn's moons, or to develop technologies for drilling through Europa's ice shell to sample its hidden ocean directly. The philosophical implications of what these missions might discover touch on some of humanity's deepest questions about our place in the cosmic order. If we detect signs of life in these alien seas, it will mark the end of Earth's cosmic loneliness and the beginning of our understanding of ourselves as part of a larger community of living worlds. Even if we don't find definitive evidence of biology, the mere fact that such environments exist and remain stable over geological time expands our conception of where life might take hold throughout the universe. The technical innovations developed for these missions will find applications far beyond planetary exploration. The radiation-hardened electronics designed to survive in Jupiter's hostile environment will improve satellites and spacecraft operating in Earth's radiation belts. The precision navigation techniques required to guide spacecraft through complex gravitational fields will advance our ability to explore the outer solar system and eventually reach nearby stars. The materials science advances needed to create instruments that can operate reliably across the extreme temperature ranges encountered in the outer solar system will contribute to technologies here on Earth. The communication systems that must transmit detailed scientific data across hundreds of millions of miles will push forward our capabilities in deep space communication and may eventually enable real-time conversations with human explorers in the outer solar system. As we stand at the threshold of this new era of discovery, we're reminded that exploration is fundamentally about expanding the boundaries of human knowledge and understanding. Every question we answer about these distant worlds teaches us something new about the processes that shape planetary systems throughout the universe. Every mystery we solve brings us closer to understanding our own planet's place in the cosmic story and the factors that made Earth a suitable home for the emergence and evolution of life. The spacecraft approaching Jupiter carry with them the dreams of generations of humans who looked up at the wandering lights in the night sky and wondered what they might be. From ancient astronomers who tracked the movements of planets through the constellations, to Galileo, peering through his primitive telescope, to modern scientists designing instruments of incredible sophistication, each generation has built upon the discoveries of those who came before. As we reach the end of our cosmic voyage tonight, we find ourselves forever changed by what we've discovered in Jupiter's magnificent realm. From Io's sulfur-painted volcanic landscapes to Europa's hidden oceans that may harbor life, from Ganymede's magnetic mysteries to Callisto's ancient scars, we've witnessed a symphony of worlds that defies imagination. These aren't just distant objects in space. They're dynamic laboratories where the fundamental processes of planetary evolution continue to unfold before our eyes. The robotic ambassadors racing toward these alien shores carry our deepest questions and highest hopes into the darkness, promising revelations that may answer humanity's most profound question: are we alone? Sweet dreams, fellow cosmic travelers, knowing that the universe's greatest secrets await discovery in the gentle dance of worlds around the giant of our solar system.